Hello and welcome to the course of Digital Image Processing using Python. I am Ahmad and we will discuss lookup table for point pixel operation, implementation, and then grayscale slicing, and then bitplane slicing. Okay, first a short review of last lecture. We discussed point pixel operation in detail, but right now we have a gamma function for revision. First, this straight line is plotted using gamma value equal to 1, and all the lines plotted above this straight line are plotted using gamma value between 0 and 1, like 0.3, 0.4 and 0.6. And similarly, all the lines plotted below this straight line are plotted using gamma value greater than 1, like 3, 4 and 5. So more important is how we interpret these functions. Like how we map the input image using the transformation to the output image. Let us consider a blue line, this one with gamma is equal to 0.6. 40% of the darker gray colors or gray shades are mapped to the 80% of the approximately 80% of the gray shades. So that's called transformation. We pick a grayscale from this image, we use this mapping to transform that gray level, and then we place that gray level in the output image. So the output image will definitely contain more brighter shades compared to the input image, because this transformation is in fact stretching or mapping a narrow range of darker shades to a wider range of gray colors, which definitely includes brighter colors. Now, this is the output of gamma function or gamma transformation using value of gamma is equal to 0.6. Sorry, this blue line is plotted using gamma is equal to 0.3. And similarly, this output is generated using gamma value equal to 0.4, and this output is generated using gamma value equal to 0.3. So now radiologist can identify spinal injury, which was in fact initially hidden in the darker shades, are originally represented using narrow range of darker shades, which are then enhanced. And the image gets more and more brighter with smaller values of gamma. So second is the case of an aerial image which is faded due to direction of sunlight and was not avoidable based on the view requirements and the direction of the sun at that moment. So we want to darken this image, and we will use gamma transformation with gamma value greater than 1. Let's take example of the curve with gamma value equal to 5. This one. So the last 20% of the brighter shades, like these colors, this range, this is the last 20%, are brighter shades, because 255 or 1 represents the white color, are mapped on more than 80%, like on this range, because this point connects this point on y-axis. So this range is mapped on a wider range of gray levels. So this is like inclusion of more and more darker shades. So if we apply any of these transformation on this image, we will get some darker image. Like this is the original image. This is the output of this transformation with gamma is equal to 3.0, then with gamma is equal to 4.0, then gamma is equal to 6.0, this one. So this image is very clear, and mostly the contents of the image on the horizon are more clear, are more enhanced with greater contrast. So, solution of the task which I shared in the last lecture. So I shared this task at the end of last lecture. Here is my solution. But remember, this is not the only solution. Let's start with the given image which is shown on the right top location. First, we need to note the composition of gray levels, and that is possible with histogram computation. Like we have the histogram of this image, and this image is grayish, and we get the same histogram which clearly depicts that this image contains only grayish gray colors. Now, next is the selection of R1 S1 and R2 S2 to enhance or to convert this low contrast image to a high contrast image. So here is my choice. Mostly gray levels are present in the range of 80 and 130. So I have selected 4 values, 80, 0 on x-axis and 130, 255. So this is like a simplified solution. This way I have to model only one straight line, whereas in this case I have to model 3 straight lines. Now we can write the equation of straight line using 2-point form, which is in fact s minus s1 is equal to s2 minus s1 over r2 minus s1 r1 into r minus r1, and this value s2 minus s1 over r2 minus s1 r1 is the slope of this line, and we have selected s1 r1 as 1 point. So overall this form is called 2-point form of a straight line. So by plugging r1 s1 r2 s2 in this equation, we get this result: 255, 130 minus 80 and r minus 80. So by simplifying, we get this form, and with little approximation, which is like addition or subtraction of one gray level from these two values 80 and 130, we can get this result, because it's like if we have 51 over here, we can have 5, exactly 5 as an integer in our answer. So this is very simplified transformation with no fractional values, and then we can write overall transformation as a piecewise linear transformation. So we have to map all the values less than 80 to the 0, and all the values between 80 and 130 as using this transformation, and then all the values greater than 130 to 255. So this portion of the transformation is represented using this expression, and this portion of transformation is represented using this expression, and similarly this portion of transformation is represented using this expression. So we can implement this transformation using an if-else statement in any programming language. After applying this transformation, we get a high contrast image on left bottom of this image, Now we can convert this image to a binary just by applying a simple thresholding technique, like convert all the pixels less than 127 to 0, and then all the pixel values greater than 127 to 255 or 1. So it's a binarized image or binary image. So let's talk about lookup table. A lookup table is just an array in terms of computer programming language that holds values which would otherwise need to be calculated. So it works like a mapping between two quantities, but mathematically it's a function of variable. So one way is to calculate values when required in program, and other way is to calculate values once and save in an array and use that array as lookup table, like this one we have. So these are called indices and these are called values. It's like input and output. A relationship between input and output, or a function between x and y, are two variables. So we can implement any mathematical function, a piecewise linear function, a piecewise defined function, or any mathematical function as a lookup table, and we can save that lookup table or values in an array, and we can use that array as transformation. Here's the Python code to calculate piecewise function we derived for our problem earlier. So the important is these two functions. So we have defined a LUT, a lookup table function, to calculate lookup table. We declared an empty array of zeros, txlut, which can be used as transformation later on. A single for loop over values from 0 to 255 iterates to fill array within if-else statements. Just to implement a structure, this piecewise linear function which we calculated earlier. So we are simply implementing this function in if-else statement. If the value is less than 80, like this one, save s equal to 0. Else if value is in between greater than 80 and less than 131, implement the transform which we calculated earlier. And if the value if value is greater than 131, save 255. Then save that value to this array and return that array as a transformation. The values stored in this array are shown on the right side of this slide. Just a selected range, from 78 to 146, and definitely the loop is iterating from 0 to 255, but I have displayed only a small range from 78 to 146. So these are the calculated values. These are the indices, and then these are the calculated values which are stored in this array txlut and is returned from this function. Next is the implementation of this transformation. How we implement this lookup table or transformation on some image. So we are after definition, transformation is the function name, and then we are getting two input arguments like image and then tx or lookup table. Then we can read dimension of the image by using shape attribute available in NumPy library, and then we have created a new image of same size of the size of input image, and then we need a nested for loop to read each pixel value, like a loop over I and loop over j. It's like loop over width and loop over height. And then this line 35 is important. Image ij will return the pixel value, which will be passed to this lookup table, and this lookup table will transform the value. Like, say we have a value 95 of the input image, then this 95 value is transformed to 75, and this 75 value is saved in the same location of the new image. And then after completion of this nested for loop, we will definitely get a transformed image, transformed based on this lookup table or this lookup table, which is calculated in fact over here. So I have skipped the code or Python code to plot and show these graphs and images, but you can consult last lecture where we have discussed the code with plotting functionality. Image on the bottom left is the input image. This is the input image. This is the histogram. That was the transformation we derived specifically to stretch the contrast of this image, and then this range of gray levels is transformed to the entire range, and this is the output image in the top left corner. So in fact this image is the contrast of this image is stretched using piecewise linear transformation to get this image. Intensity level slicing. This topic is perfectly related to piecewise defined functions, as we discussed earlier, and the lookup tables. But the concept is about objects within the image. Say for instance we have an image with certain object represented by a contiguous range of gray levels, and we want to mask that object. Then intensity level slicing is the solution. This concept has very vast application, like in satellite imagery and biomedical imaging. First let us know how we can implement these transformations. There are two ways in general. First is and the simplest one is to assign a fixed range of grayscale, say to a value 255, and rest of the grayscales to some other value, say 0. So we are just masking this range of gray levels. That's like converting a certain range of gray levels to a one grayscale and all other gray levels to some other range. And then there is another way, like assigning a fixed range of gray levels from A to B to a certain value, say 255, which is white color, and leave all the other intensity levels in the image unchanged, like a straight line, which is represented by a straight line. So each intensity level is mapped to the same intensity level, whereas this range is masked or represented with a fixed gray level. So this is called intensity level slicing. Let's see an example. So this is an example figure. This figure is an aortic angiogram near the kidney area. The objective of this example is to use intensity level slicing to enhance the major blood vessels that appears lighter than the background, like these blood vessels. So the image on the leftmost position is the original image. Image in the center is sliced using simple method of binarization, like the gray levels used are represented. These vessels are represented using a range of gray levels, which are mapped to say 255, a white color, and rest of the image is in fact mapped to a black color. And the image on the right side is sliced using second method, where we slice a range of gray levels, gray scales, which is of interest, and then left remaining intensities unchanged. So these are the two ways to detect an object or to enhance an object. So the same application can be used in aerial images or space images. Here is another example. A grayscale slicing over near infrared imaging helps in locating veins for venipuncture by overlaying videos on the human body. So our next topic is bit plane slicing, and as we know, each digital image is represented using a fixed length binary numbers. Say for instance, we have an image whose each pixel is represented by 8-bit binary number. So we can extract 8 different binary images represented by each bit location, like an image represented by most significant bit of each pixel value. And similarly, we can make another binary image from the same image using a least significant bit of each pixel. So this is called bit plane slicing. Slicing based on the significance of the bit or location of the bit. So it's like if we have an 8-bit image, we can make 8 slices. If we have a 3-bit image, I mean all the gray levels are represented using 3-bit images, then we can make 3 slices. One with the most significant bit, one with the least significant bit, and one with the center bit, because each pixel is represented using 3 bits. Here is an example. We have this image, and in bit plane slicing, the higher order bits, I mean the most significant and the higher side of the bits, usually contain most significant or visual information, whereas the lower order bits, like least significant bits, contain subtle information or subtle details. Here is the 8-bit plane sliced images of the image shown on last slide. This image. Top left, this is generated using most significant bit of each pixel value. It is like binarization of an image using 127 as threshold value. So all the pixel values less than and equal to 127 are mapped to 0, and similarly all the values greater than or equal to 128 are mapped to 1. So we get this image. This is called most significant bit plane, and this is the next significant bit plane, like 7th bit, and this is the 6th bit, 5th bit, 4th bit, 3rd most significant bit, 2nd, and this is the least significant bit plane. So it does not mean that LSB contains only the noise. Yes, there is a huge chance that LSB gets noise, considering sampling and quantization. When we apply compression algorithms, this noisy nature of LSB, in fact, severely limits compression capabilities. So we use bit plane slicing for image compression. We can drop this bit, like are these two bits. Even then we get huge information, a better information, um, with very small amount of data. Here's another example of a bit plane slicing. An 8-bit grayscale image of $100 US dollar currency note, and this is the original 8-bit grayscale image. This is the most significant bit slice, and then 7th, 6th, 5th, 4th, and then 3rd, 2nd, and this is the least significant bit. So you can observe this is almost noisy bits. There's very less information, whereas these bits are clearly representing most of the information of this image. So here is the original image. This image is constructed using 8th and 7-bit plane, and similarly this image is constructed using 6th, 7th and 8th bit plane, and this image is constructed using 5th, 6th and 7th bit plane. So you can observe the dynamic range of this original image is better than these images. I mean, the representation of black color and the representation or contribution of white and black color is better in original image as compared to these reconstructed images. But important is that these images are represented using very low, very small size of data, like 20 or 30% of the data. On the other hand, these images are not like binary images, so very comparable in information, in representation, but with lesser amount of data. So next is how we can implement or how we can extract bit plane images. If you know little about bitwise binary operation, bitwise operators in Python or C language, then you can mask each bit using a for loop. So you can mask for the most significant bit, and similarly you can mask for the least significant bit, and then you can reconstruct using and OR operators. So hopefully it's not a difficult task, and you can perform the same task in Python language, considering any image as example. So let's stop this video over here. In the next video we will discuss about histogram equalization, specification and matching, and goodbye.